Hi guys, Miss Peterson here for video 2 of our lecture on solubility equilibria. Okay, this is part 2. In the previous video, we talked about what solubility equilibrium was, how we write equilibrium expressions, we practiced a little bit, and looked at the chart that you can find in any chemistry textbook, and we did some practice on calculating some basic solubility equilibrias given the concentrations. In this video, we're going to learn how to calculate the solubility given the Ksp value, which is a lot more common of a calculation that we'll do since these solubility values are mostly known to us. Okay, so whenever they say solubility, what they mean is the molar solubility, aka how many moles will dissolve per liter of solution. And there's a really convenient way to do this called an ice table. First, I need you guys to fix a typo for me. Calcium phosphate is Ca3PO4 2. Okay, so make sure you fix that on this problem. It has a Ksp value of 2.0 times 10 to the 29th, and we're going to find out its solubility. We're going to find out how many moles of calcium phosphate dissolve per liter of solution. So let's look at this dissolving process. We have our calcium phosphate, and it will break up into 3 calcium 2 plus ions and 2 phosphate, which is PO4 3 minus, 2 phosphate ions. Now, we're going to set up an ice table. ICE. What this stands for, I is your initial, the initial concentration. So say we have X moles of this in our solution. Before any of it dissolves, we don't have any calcium or phosphate ions. Those are just 0. C stands for change. So when equilibrium happens, you're going to lose X moles of that calcium phosphate. When you do that, it breaks them into 3 calcium ions. So you're going to get 3 times as much calcium ions as you had the concentration of the calcium phosphate. For the phosphate, you're going to get 2 times as much. Okay? So that at equilibrium, for whatever amount dissolves, we're going to have no more of that, 3 times the concentration of the calcium, and 2 times the concentration of the phosphate ions. Okay, E stands for equilibrium. Okay, so initial, change, equilibrium, we call them ice tables for short. So we're going to use this to figure out what the concentration of the calcium phosphate is that dissolves. We're going to use it to find that X. So we need to write our equilibrium expression. Ksp equals the concentration of calcium 2 plus ions. Because there's a 3 there, it gets raised to the 3rd power. Okay, times the concentration of our phosphate ions raised to the 2nd power. Okay, now we plug in our values. Our Ksp is 2.0 times 10 to the 29th. So we know that X is going to be really, really small. That's a low Ksp. That means very little of it dissolves. Okay, so 2.0 times 10 to the negative 29, okay, equals, at equilibrium, our concentration of calcium is 3x raised to the 3rd power, times our concentration of phosphate, 2x, raised to the 2nd power. Okay, so now we need to simplify this down. 3 cubed is 27. Okay, so we have 27x cubed times 2 squared, which is 4x squared. Okay, and then we can combine those. 27 times 4 is 108. And then you need to remember your rules of exponents. When you're multiplying exponents, you add them. So it'll be 108 x to the 5th. Okay, so we have 2.0 times 10 to the 29th equals 108 x to the 5th, and we need to solve for x. Okay, so putting your algebra skills to the test. Divide by 108, divide by 108. So 2.0 times 10 to the negative 29 divided by 108. Okay, I got 1.85 times 10 to the negative 31 equals x to the 5th. Okay, now we need to take the 5th root of that. Okay, to undo a square, you take the square root. To undo x to the 5th, we take the 5th root. There's a couple of different ways to do this. On your calculator, you might have a button that can do it. Another easy way to do it is just to raise it to the 1/5 power. Okay, if you take the square root of something, it's like raising it to the half. You could also plug in 0.2 and get the same answer. I prefer just to do the 1/5 because we're taking the 5th root of it. So I took my answer, or 1.85 times 10 to the negative 21, to the 1/5 power. And I get that x is 7.137. So I'm going to say 7.14 times 10 to the negative 7. Okay. Now x, if you look back over from your ice table, x was your initial concentration of calcium phosphate, the amount that dissolved, the amount that changed. So this is our molar solubility. Okay, this is how many moles per liter will dissolve. If we wanted to find our moles of calcium ions in solution, we would multiply it by 3. If we needed to find the molar solubility or how much phosphate ions would be, we would multiply it by 2. Okay? Okay, let's try another one. Okay, we'll do another one together. The Ksp for calcium carbonate is 3.8 times 10 to the negative 9 at 25 degrees Celsius. We're going to calculate the solubility of calcium carbonate in pure water in moles per liter and grams per liter. So let's look at calcium phosphate. CaCO3 will break up into calcium 2+ ions and carbonate ions. Okay, we set up our ice table. This one's a little bit easier because notice all of the ratios are 1 to 1 to 1. So if we have x moles of this, no moles of there, we're going to lose x moles and gain it over here so that at equilibrium, all of that calcium phosphate that could dissolve did dissolve. And we have x moles per liter of the calcium and x moles per liter of the carbonate. Okay, now we need to write our Ksp expression. Again, since it's just 1 to 1, it's just going to be the concentration of calcium multiplied by the concentration of carbonate. Okay, now we can plug in our values. 3.8 times 10 to the negative 9 is our Ksp. Equals our concentration of calcium, which we said was x, multiplied by our concentration of carbonate, which is also x. Okay, so we have that 3.8 times 10 to the negative 9 equals x squared. To solve for x, then we take the square root of both sides, and we get, let's find out, square root of, always put your scientific notation numbers in parentheses. It helps make sure that the calculator doesn't do anything weird. Okay, so the square root of 3.8 e times 10 to the negative 9. We get 6.16 times 10 to the negative 5 moles per liter. Okay, So that's how many moles of calcium carbonate will dissolve. That's how many moles of calcium ions we'll have. That's how many moles per liter of calcium carbonate we'll have. Now, if it asked us for the solubility in grams per liter, because we measure things out in grams, all we would have to do is convert this to grams. So this, remember, is our concentration of calcium carbonate, our molar solubility of calcium carbonate. Let me show you how to convert it to grams. I'm going to get another color for that. Okay. So how do we convert from moles to grams? Molar mass. So we have, nope, this one doesn't work. Okay, give up. I'll just do it in green. Okay, so we have our 6.16 times 10 to the negative 5 moles per liter that will dissolve, and we want it in grams per liter. We know that 1 mole of calcium carbonate has a mass of, let's see, calcium is 40.08. Double check on my periodic table here. Yep, calcium 40.08 plus carbon 12.01 plus 16 times 3, because we have 3 oxygens, 100.09. Okay, so the moles cancel out. We multiply it. Oops, delete that. And we get 6.165, so I'm going to say 6.17 times 10 to the negative 3 grams per liter. So there is our solubility of calcium carbonate in moles per liter and grams per liter. Okay. Again, the trick for these is just to practice them over and over and over again. Okay, so I want you to try this next one on your own. Okay, calculate the solubility of copper 2 iodate. Okay, iodate, if you're unsure, it's IO3 minus. Okay, so I'll help you out, help you get started by writing the how it dissolves. It'll dissolve into copper 2 plus and 2 IO3 minuses. Okay, so go ahead and set up your ice table and your equilibrium expression and try it on your own. Okay, so you should have gotten 3.3 times 10 to the negative 3 moles per liter. Go ahead and check your work. And if you have any questions, I will answer them in class. Okay, now I want to talk about one more issue called the common ion effect. Okay, so this one says to calculate the solubility of solid calcium fluoride, which has a Ksp of 4.0 times 10 to the negative 11. So a very small Ksp, that means very little calcium fluoride is going to dissolve in a 0.025 molar NaF solution. So the main difference here is there's some fluoride ions, this dissolves, so there's some fluoride ions already in solution. Let me show you how that affects our solubility. So we have our calcium fluoride, okay, and it is going to dissolve a little bit into calcium ions and fluoride ions. Just like in all the other problems, we set up our ice table. Okay, we have X moles of calcium fluoride initially and no moles of calcium. However, we have moles of fluoride, okay? So if this is 0.25 molar NaF, that means it's 0.025 molar Na plus and F minus. So we have to put that here, 0.025. Okay, so some of this is going to dissolve. Minus X, we're going to add X of our calcium and 2X of our fluoride. So that at equilibrium, all of that calcium fluoride that could dissolve dissolved. We have X moles of calcium and 0.025 plus 2x moles of our fluoride ions. So let's go ahead and write our Ksp expression. Okay? Our Ksp equals our concentration of calcium ions multiplied by our concentration of fluoride ions squared. Okay? From the 2 there. Plug in our values. 4.0 times 10 to the negative 11 equals x times 0.025 plus 2x squared. Okay, so you can see how this math could get super tricky. We would end up with a quadratic, okay? But we can simplify it. Ksp is super, super small. That means x is going to be super, super small. Like 10 to the negative 11, that's 0.0000000. Okay, 9 11s. No, 10 zeros before you get to the 4. That is going to make such a small difference compared to 0.025. Such a small difference that we can ignore it and it really won't change our values, okay? Because it's going to be so small comparatively. Now, it makes our problem a lot easier for us to solve. So now we have 4.0 times 10 to the negative 11 equals x times 0.025 squared, which is 6.25 times 10 to the negative 4. Okay, we divide 4.0 times 10 to the negative 11 divided by that number. You can just put answer since it's already in my calculator. And we get 6.4 times 10 to the negative 8 equals x. Okay, so a lot less of the calcium fluoride dissolves. If you remember a little bit of the Chatelier's principle, if you have more of this, it shifts the equilibrium toward the solid so that less dissolves. It's a much lower number than what we would get if it was in pure water, if we didn't have that 0.025. Okay, but you can do that. Such small amounts dissolves that we just ignore it when we do the calculations. Okay, so that's how many moles per liter you have. Okay, cool? Okay, cool. Now, the last thing we have to talk about is the reaction quotient, Q. Basically, Q is K, but not necessarily at equilibrium. Okay, it's used to predict what will happen in the solution if the ion will form. Because if you don't have enough ions in the solution, okay, they're just going to be too far spread apart, and you're actually not going to get a precipitate if the reaction quotient is less than the Ksp. It's not saturated enough for the precipitate. Okay, so we use that a lot to figure out when things will form. Okay, so let's go ahead. This is a pretty difficult problem, but I think we can do it. Let's go ahead and I'll show you guys how to solve this one out. Okay. A solution is prepared by adding 750 milliliters of 4 times 10 to the negative third molar selenium nitrate to 300 milliliters of 2.0 times 10 to the negative 2 molar potassium iodate. Will, I think that's cerium, sorry, not celerium. Will that precipitate? Okay, we're given its Ksp. So, let's look at what we are given. Okay, we're given that we have CeNO3 being mixed with KiO3. Okay, and we know the solid precipitate that we're going to get is CeIO3. So CeIO3, 3. And then we'll have some potassium nitrate, KNO3. Always a good idea to get in the habit of balancing your equations. So we have a 3 there. We're going to need a 3 there, but then we have 3 potassiums, which is cool because we have 3 nitrates. So we're going to get a 3 there. Let's keep on writing the information that we're given in the problem. Okay. Because molarity is in moles per liter, I highly recommend that you just automatically change anywhere you see milliliters to liters. So this is actually 0.750 liters, and this one is 0.300 liters. Okay, so we have 0.750 liters of 4.00 times 10 to the negative 3 moles per liter solution of this, with 0.300 liters of 2.00 times 10 to the negative 2 moles per liter of the KiO3. And again, we're looking for this solid. So, step 1. Let's figure out, if we're looking for this one, okay, let's figure out how many moles of iodate we have and how many moles of cerium we have. Okay, so moles of Ce is what I'll find first. Okay, we know we have 0.750 liters of our solution. Okay, I'm going to zoom in so you guys can see what I'm doing a little better. Okay, and for every 1 liter, we have 4.00 times 10 to the negative 3 moles of our CeNO3. Okay, then it's a 1-to-1 ratio. For every 1 mole of this, we have 1 mole of this. 1 mole to 1 mole Ce. Okay, when we plug that into our calculator, 0.750 times 4.00 times 10 to the negative 3. Oh, wait. Highly recommend putting things in parentheses. In practicing this problem, I got a little messed up because I wasn't putting things into parentheses. So always put your scientific notation into parentheses. Okay, and I got 3 times 10 to the negative 3. Okay. Now in green, I'll figure out my moles of iodate, because again, that's what's going toward forming my, my precipitate. Moles of IO3. Okay, so we have 0.300 liters. For every 1 liter, we know we have 2.00 times 10 to the negative 2 moles. And it's the KiO3 that is our solution, so that's also a 1-to-1 ratio. Okay, for every 1 mole of KiO3, we have 1 mole of the iodate ion. So we plug that into our calculator. And we get 6.00 times 10 to the negative 3 moles of IO3 minus. Okay, so now we need to see if that is enough to form our precipitate. So I'm going to go ahead and look at the net ionic equation to write the Ksp expression. So the net ionic equation is we have our Ce ions coming together with 3 IO3 ions to produce our CeIO3 3. Okay, that means our Ksp expression would look like concentration of Ce times our concentration of IO3 minus cubed. Okay, so we could find our molar solubility of our compound using that. But right now, we're going to calculate Q instead to see if the Q value based on these concentrations is greater than or equal to the Ksp value. So it's the same formula. Okay, Q equals concentration of cerium times the concentration of iodate cubed. So let's plug in our values. Q equals our concentration of CE. Ooh, okay, I lied. We don't quite have our concentration of CE yet. We need to divide it by the number of liters that we have. So in our solution, we have 0.70 added to 0.30. So we do have 1.050 liters of our solution. So we need to remember to convert from moles to the molarity when plugging into our Q value. So I'm just going to do that here in this step for you. 3.00 times 10 to the negative 3 moles per 1.050 liters. Okay. Then 6.00, running out of room here, times 10 to the negative 3 moles of our iodate divided by 1.050 liters. And we have to remember to raise that to the third power. Okay. So lots of calculator stuff. So Q equals 3.00 times 10 to the negative 3 divided by 1.050. Okay, so we got 2.857 times 10 to the minus 3 times, okay, we have 6.00 times 10 to the negative 3 divided by 1.050. Okay, and that's raised to the third power. So to the third power, 1.865 times 10 to the negative 7. Okay, multiply it by this value times 2.857 times 10 to the minus 3. We get a Q of 5.33 times 10 to the negative 10. Okay, now we need to compare that to our Ksp value. Our Ksp value is 1.9 times 10 to the negative 10. So our Q value is greater. So Q is greater than Ksp, which means yes, we will get a precipitate. Okay. The last problem we'll do in class, go ahead and try it. It's a little complicated, but I think you guys can do it. Okay, cool? Okay, cool.